Hi everyone, so let me get to maximize this screen. So in this lecture, I will tell you how you actually do these modulation and demodulation in an actual circuit. Because, well, in the circuit, it seems like we need some low pass filter, we need some diodes, right? But how do we do multiplication, right? On a circuit, it's kind of easy to add two signals together, right? We actually even have these summing amplifiers, right, where you have, maybe like signal 1, signal 2, right, signal 3, and these will have different resistor values on it. Sorry, right, and this will give you different output, right, depending on it can sum up basically, signal 1, 2, 3 together, right? But how do you do multiplication, right? We haven't really talked about how that happens. Okay. So multiplication in analog electronics is done using diodes. The reason we use diodes is because when it's transitioning from the non-conductive to the conductive phase, I guess I should have drawn this, right? Right, voltage versus current. Remember this for a diode, right? It's basically 0, 0, 0. It's not 0. It's actually, this is the saturation current, right? And then it turns on like this, right? Where this is around what the diode voltage is, okay? But in this part, this is an exponential, right? Using the diode law that we talked about on chapter 3, I think. Okay. But when we start talking about op amps, what happened is that what you can do instead of an inverting amplifier where you put a resistor here, right? Because this could be anything you want, right? It can be a capacitor, which makes it a low pass filter. No, makes it a low pass filter, or it can be a diode. Okay, if you put in a diode in there, what you're going to be amplifying is you're basically going to be amplifying this turn on curve at the as the current changes. Okay, and since the current versus voltage is an exponential, voltage versus current will be a natural log. Okay, and that's how we can do logarithm in a circuit. Okay, and why are we doing a logarithm? It's because let's see, make sure we're recording. The reason we're doing logarithm is because, right, you have the log identities where if you take the log of some function A plus the log of some function B, which you can do by just adding two of these signals together, right? Once you add them together, it's actually the log of the product of A times B inside the logarithm, okay? The way I remember this is that whenever I take a log of something, the thing that's inside the log, I always think about that as kind of like the exponential of stuff, right? Because when you take a log of something, you're actually just getting an exponential power of it, approximately. Okay, well, not approximately, actually, yes. Okay, so we're going to utilize this property in order to do multiplication, right? Because now you can see that, oh, well, if I want to multiply A times B, if I put each A and B inside a log, add them together, then I actually get the product between them with the log outside. So we're going to have to unlog it by exponentiating afterward. Okay. Remember that for this circuit, right, using the golden rule, I'm going to use the big I and big V here, that the current that you get is going to be proportional to whatever Vn is divided by Rn, because that's the resistor, because the current cannot travel through here. It can only go through the feedback loop, right? Okay. And this point is also tied to ground, right? Virtual ground, because the positive is actually tied to ground. Okay, so therefore, in this case, right, V out is going to be equal to whatever this function is. So for if F, this component up here is a resistor, then this will just be RF. So then you just have an inverting amplifier. But if we put in a diode instead, where the current and the voltage is not proportional to each other, it's actually related to each other through a natural log, then you actually get a log function at V out as opposed to linear. Okay, so let's put a diode there, right, in the feedback loop. Put a little diode that's forward bias, right, going from one side to the other. Okay, be a little careful. This will also remove some of the negative voltages, right, because you cannot have current going the opposite direction of a diode. You also have a little diode drop situation here. So if you do that, right, we're going to take advantage of this exponential part of the diode law, also known as the Shockley equation. Okay, let's zoom in a little bit. It's a little bit bigger, right? Remember that this current is equal to the saturation current, which is this tiny number. So typically the saturation current is going to be like a picoamp, okay, times the exponential of the voltage across that, right, divided by n. N is the idealization, right? Let's just make n equals to 1. Let's make this very ideal. And VT is the thermal voltage, right, which is at room temperature is going to be about 25 millivolt. So VT volt, right, make n equals to 1, and then IS is going to be 1 picoamp. Okay. What we can do is do a little bit of math and solve for V, because we're actually trying to invert this, right? We want to figure out how V behaves as a function of I as opposed to I as a function of V. Basically, it'll turn it into a log function, because in order to get the V out of the exponential, you take the log of both sides. You're solving for V, not little v, right? V will become basically whatever the thermal voltage is, times the natural log of 1 plus the ratio between the current traveling through the diode divided by the saturation current. And since the saturation current is going to be small, right, we can assume that, well, we make this approximation that IS, so I over IS is going to be much bigger than 1. So therefore, in this natural log term, right, the second term actually dominates, so the 1 doesn't actually matter. So we can simplify this equation to be basically V equals to the thermal voltage times the natural log of the ratio of the current over the saturation current. Okay. If we go back up here, right, that's the functional form, right, this function that we're dealing with. Okay. So if we do that, right, where we force I to be Vn over Rn once again, right, so this I goes up here, right, so V out is going to turn into basically negative Vt because of this. This is just an inverting amplifier. Natural log of Vn divided by Rn times Is, okay, on the denominator. So, but the important thing is that basically now you have a V out that's proportional to natural log of Vn, right? That's what you want. Okay, so now you have a circuit that basically whatever your input is going to take the natural log of it. Well, the output is going to be proportional to the natural log of it. Okay, so going back all the way up here, right? So accomplished, right? We can do this natural log stuff now. Okay, so what you do is then, well, of course, you have two inputs, right? If you want to multiply two things together, you need two of them. All right, to multiply these two things together, you have two of these circuits, right, taking natural log of it, and then you pipe that output into a adder, an adding circuit, right, through an op amp, and that will allow you to, the output of that is going to be the natural log of the product between A and B, right? So instead of A and B here, we're talking about, right, this is going to be, the A is going to be the signal, the B is going to be the carrier function, right? Okay. Of course, in order to undo this logarithm, right, because in the end, you don't want the log of Fs times Fc. You want Fs times Fc by itself, right? The way you do this once again is you use the diode once again, and this is actually much simpler. You don't even need to amplify it. If you pass the signal through a diode with a resistor, the V out here, right, big V, is going to be proportional to the exponential of the natural log of A and B. Okay, And then if you natural log, exponentiate natural log, you undo that natural log, and then you just get A and B back. Okay. So those of you who are interested in how this design actually happened, and there's a lot of engineering and consideration you have to go through to make sure it actually works properly within its parameter. I suggest that you read this little analog multiplier PDF, which is where I grab some of these information from, but I kind of just summarize a lot of the stuff for you and simplify things that, just to get through the math. Okay, so this is how your 8633 multiplier chips work, the one you saw previously on there also. The documents is here on analog.com if you want to use that one. You can also look up other data sheets, so it'll be similar. Okay, it's a 8-pin chip, and the left end here are the inputs. So this is the X input, this is the Y input. In this case, what we're going to use it for, we're going to make this the signal, we're going to make this the carrier. Okay, these are differential inputs, so you could have a differential input, but what we're going to do is we're going to have this as just a single-ended, meaning we tie basically, X to the ground, Y to the ground, and then you just have a single-ended signal instead. Okay, what it does to these two input is that it multiplies it together, right? And then it outputs it over here as W. Okay, W pin 7 is the product between FS and FC. Okay, of course you need to power this up with some power supply, which is just pin A and 5. Z here is an offset in case you need to shift the signal up and down. You can actually do that if you want. Okay, that's why this little summer is here. So it does the multiplication, and then it undo it by taking the using the log, the natural log behavior of the diode, and then it undo that by basically exponentiating things. Okay. So in order for this to work properly, there's some specification. So what the output is, right? This W that you're talking about, right, on pin 7. Okay. So it takes the difference between the two inputs. So in our case, X2 and Y2 is going to be 0 in the lab, but it can be a differential input. So X1, let's say you put in 5 volt as X1, 5 volt as Y1, right? The product between them is going to be 25. And what the chip actually does is actually it divides it by 10. So your output is actually 2.5 volts. Okay. So you're going to have to take that into consideration when you're dealing with these multiplier chips. It actually divides all the time by 10. The other thing it does is that it also allows you to have an offset if you need to. I don't think we need it in our lab, but in case you do need it, you can have an input offset. Let's see. What's the other ones? Okay. So the input has to be between 10, minus 10 to 10, so it cannot handle anything beyond that. So don't put in 12 volts in there at the input. The supply voltage is plus or minus 15. So supply voltage plus or minus 15. The signal between negative 10 to plus or minus 10. Okay. So don't mix those two up. The output can only go up to 11 volts. So if you put in 10 times 10, that will give you 100. Divide by 10, it should give you 10 as the output. So it should stay within the output needed. If you don't do something really weird, like shifting it up by 10 volts or something like that. Okay. On this plot, this is the output response, meaning it's kind of like the attenuation plot that we've been looking at, right? It's basically how well this multiplier behaves as a function of frequency. So you can see here, basically, remember like 0 decibel, that means a gain of 1, right? So this works really well, right, up to maybe 300 kilohertz, okay? So you probably don't want to use anything more than 300 kilohertz in this circuit here. Okay, so how do we do full modulation with this particular chip, right? Remember, the goal is that we want to multiply our signal with our carrier, right? Okay, so to multiply your signal with your carrier, you put the signal and the carrier as input on the left-hand side of the chip. Oops, circled the wrong thing. Okay, right. Since we're using single-ended input, right, you just tie the negative input to the ground. Okay, and also, since you don't actually need an offset, you tie that to ground. Make sure you power it up with plus minus 15 volts. And then basically the modulated signal will come out of pin 7 on your chip. Okay. Okay. So this side does the modulation. Right. Okay. And then you can also demodulate it with a second AD633, right? By just having that modulated signal go straight into the input of the other one, right? Right. In order to demodulate, of course, you need the carrier, right? You don't need the signal, you need the carrier, okay? And this is connected in a similar way, and then the demodulated signal will actually come out of pin 7 once again. But remember, this is a combination of high and low frequency, right? Then you put this through a low pass filter, right? Can be inverting or not, right? Let's just, I'm not going to try to remember exactly how this, which order to put the capacitor versus the resistor. So, but this is, you want to put this through a low pass filter, and this will be basically proportional to what your signal is going to be. Okay. So as I noted on the theory side of the lecture, right, this works because we are able to connect the function generator that gives us the carrier signal on both chips. Okay, but if you're sending this over on the range of like 1,000 kilometers, so let's say you're sending this to a satellite in space, right, you don't have the same function generator on both ends. Okay, so this is where the lock-in mechanism work, where it actually locks in the correct frequency and the phase. And in the lab, I'll have you play around with that to see how much a slight difference in frequency and phase actually degrades your signal. Okay, but in the lab, since you're on just one breadboard, you can do that. One thing to note is that the way you would want to do this, right, is that on your function generator, you want to split the signal right at the function generator and make these two cables the same length. Okay, so this will go to your modulator, and you want this to go to your demodulator, because if the cables are different length, because the speed of light is finite, right, you will get out of phase with each other. Okay. All right, so the last thing I want to cover is actually something a little bit simpler, and actually how AM radio works. It's actually using, instead of using this full modulation method that we're talking about, it actually uses this partial modulation. Okay, it's going to work very similarly. But so why do we have to have this? Why do we use partial modulation on radios instead, AM/FM radios? So AM radio. So since we're doing amplitude modulation, that's what the AM stands for. Okay. Remember that in order for the modulation to work properly, right, you need a multiplier on one end and then a carrier frequency on one end. You need a demodulating multiplier on the other end, and you need exactly the same frequency on the other end also, right? And since if you're sending this wirelessly, you don't have a cable between them where you can share your carrier signal, your carrier wave. Okay. And in order for this to happen with your internet modem, which has this phase lock loop, right, in it, right, these phase lock loop is going to be a little bit expensive. That's why if you don't return your internet modem, they're going to charge you $150 for it. A lot of that is actually in this phase lock loop circuit and the multiplier chip. Okay, but with partial modulation, you do not need this phase lock loop. and you don't need the the second multiplier, which makes it cheap enough that when I was a kid I was able to just buy a little AM/FM radio for about $5. So I mean these AD 633 chips, each of them already are like $5. So there was no way someone will be able to sell a $5 radio if that's the case. Okay. So in order to do partial modulation, both the modulator, the sender, and the receiver has to agree on something. So this is more of a one-way communication where the radio station will send the information, and on the other end, all you're doing is receiving. So your television, your radios, they all kind of work like this. This only works for one-way communication. In order to do two waves, you need to do the full modulation. Okay. To do partial modulation, the first thing you need to do is that you need to put an offset on your signal, basically by shifting it up so that the signal never crosses 0 volts. Okay, so in black here, right, this is the partial modulation signal, where it's the same cosine wave, but it's shifted up by its amplitude, so it never crosses 0. In fact, a lot of times what you want to do is actually stay away from 0, maybe like tenth of a volt above 0, so therefore you actually never close to it. Okay, right. The rest works kind of the same. So the amplitude is going to be AS, and then you just have this one amplitude shift above for your cosine wave, so that it never crosses 0. Okay, and then you do the same thing. You multiply this, right? This partial modulation, right? It's basically Fs times the carrier, right? And remember, this carrier is just some cosine function times t. Okay. Now notice here that you still have the wiggle that we talked about first, right? But let's look at the lobes, right? So I'm gonna use black here, right? So the period of your signal, let's say it starts here, it goes up, it goes back down, and now we're at the same point, right? Because it's going to be going up. So this is one period, right? T partial, right? Okay, notice that for every period, you have one lobe, right? So each lobe actually tells you one period. And you can see that the shape of the lobes are actually exactly what the shape of your partial modulation signal is supposed to be. So this is really cool because this makes things a lot easier, right? Because now the partial modulated wave, the only thing you need to do is actually put it through a low pass filter, right? That'll basically get rid of all these wiggles, right? And gives you the low frequency part. Oh, I forgot. And also you don't want these negative stuff, right? So plus a diode, okay? Because if you put it through a diode, then it can actually knock out half the wave, right? Just like we did in the halfway rectifier, okay? So this is how partial modulation work, where it's a one-way communication where you just send the signal, and then the other side, all it needs is basically one resistor, one capacitor, probably an amplifier, right, in order to amplify, because the signal will be smaller in amplitude by the time it gets there, and the diode. So you need those 4 devices, and those 4 things would cost less than $1 to buy, and the rest of the cost will just be breadboard and stuff like that. Okay, so how does the partial modulation circuit work? So the modulating side, the left-hand side here, is basically the same. Connection is the same, but your Fs, right? I'm just copying that over. Sorry about that. Right? Has to be shifted up. Has to have this offset. Okay. So if the amplitude of your wave is 1 volt, you have to shift it up by maybe 1.1. You want to stay away from 0, right? If the amplitude is 2, you need 2.1, and so on like that. Okay. And what that does is that it sends out this partial modulated wave out. And what we're going to do in the lab is actually we're going to amplify this in the op amp. This is just it's a non-inverting amplifier. And we're going to send that out through an LED. It's just going to blink, 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 blink at very high frequency. You won't be able to see it. Okay. Okay. And this light goes out and travels through a fiber optic cable. Okay. Uh, and then gets received on the other end on the receiver. Okay. What the receiver does, it basically just detects the signal. It's just a detector, which is a photodiode. Okay. And nice thing is that, well, we already have a diode in the system, so it knocks out basically all the negative voltages. Okay. And then you basically put this through a low pass filter, and then the output will be basically whatever your signal is going to be, which is really nice. The reason we do this on the fiber optic instead of just through the air is because we used to do it through the air, but then you have to turn off all the lights in the room in order to do this, because otherwise your photodiode will just get saturated by the room light. Okay, so that's how we going to do partial modulation in our class in the lab, and then I will have some practice exercise so we're ready for that in the lab next week. Okay. I think I'm not going to go through the phase and frequency modulation, but those of you who are interested in how these actually work, they work in a very similar way as amplitude modulation, but you're using the phase difference and the frequency instead of the amplitude to send the information instead. So I suggest I posted the notes from the Chinese University of Hong Kong, who has some pretty concise notes on it. So unfortunately, modulation is a huge has huge application everywhere. So you just look up modulation, you just have like information everywhere. And a lot of time today's modulation actually are digital, are modulating digital signal as opposed to analog signal. And those are a little bit harder to understand because you don't see a continuous function. So these lecture notes from Wing Kin Ma, no relation, is very useful because it's very similar to what we saw as the amplitude modulation. It's just that due to time and the fact that we're not going to do phase and frequency modulation on that. I'm not going to make everyone read through that and do the lecture on that. Okay. All right. So I will get the homework posted and these lecture posted. And that way we're ready for next week.